Well, the DC motor. I took one with me and I opened it. And when we look to that DC motor, we see two important parts. We have the fixed part, that's what we call the stator. And in that fixed part, in that stator, a magnet has been applied, consisting of a north pole and a south pole. And we have the rotating part, which we call the rotor. You can see it here on the shaft. And that consists mostly of copper windings. So when I put the rotor out of the motor, you can see it over here. We have these copper wires, and when we apply a voltage to these wires, a current will flow through these wires. And when we have a copper wire in which a current flows in a very magnetic field, then a force is applied to these wires, which is the Lorentz force, and that brings us a rotating force, what we call a torque in Newton times meter. And when a rotor turns, when it rotates, then a voltage is induced in that winding, which we call the back EMF voltage. And that back EMF voltage is proportional to the radial speed of the rotor. And when we know that, we know enough to draw the electrical circuit, and then we can draw, based on that electrical circuit, the torque speed characteristic. So let's start with that electrical circuit. What we have seen is that the rotor consists of copper wires, which we can model as a series connection of a resistance and an inductor. And when we put a voltage to this series connection of the resistance and the inductor, and we put a voltage over here with a plus and a minus, and let's call it this voltage U, then a current will flow, or let's call this resistor R and let's call the inductance L. Well, a current will flow in that direction through this winding, so through the R and through the L. And by turning the rotor, a back EMF voltage is induced in these windings, which we call the back EMF voltage, or UEMK, or in English UEMF, the back EMF force. Well, because we wanted to draw a torque speed characteristic, which is a static equation, we can neglect the inductor, and then we have a much more easier electrical circuit consisting of an R, a resistance, and that back EMF in series. So now we can write down the equation, the motor voltage equation, which says U equals I times R plus that back EMF voltage UEMK. Now you should know that this back EMF voltage is proportional to the radiant speed of the rotor. The formula, the equation for UEMK is UEMK equals K, which is the motor constant, or torque constant, or the motor speed constant. We often call it the motor constant, K, times omega, and omega is the radial speed of the motor. So we can put that in an equation, which gives us U is E times R plus K times omega. So, well, what was it again with omegas and frequencies, etc.? Well, let's draw a circle over here, rotating around the point. Well, here's my circle, more or less a circle. And when we make one revolution, then we make an angle of 360 degrees, which equals 2 times pi radians. So when we make 2 revolutions, then we get an angle of course, 2 times 2 pi, which is 4 pi radians, etc. So we can define 1 revolution equals 2 times pi radians. So in that case, we can also say 1 revolution per second equals 2 pi radians per second. So a speed of 1 revolution per second is equal to 2 times pi radians per second. So omega is 2 times pi times f, in which f is the number of revolutions per second. We also often see in data sheets is that we don't use omegas or f's, but we use the n, and the n is the number of revolutions per minute. And then we can replace the f by n, the number of revolutions per minute, divided by 60. So in that case, omega equals 2 times pi times n over 60. Right. So now we have that motor voltage equation, but there is another important equation which gives us the relationship between the motor torque, T in Newton times meter. T equals the motor constant, K, times the current which flows through the windings, the current I. That K is the same K as in the back EMF. So T is K, the motor constant, times I. So there is a direct relationship between the motor torque T and I, the current I. So you can also rewrite it the other way around. I is the motor torque T over the motor constant K. So you can substitute that in the motor voltage equation, and then we get U is T over K times R plus K times omega. Remember, omega is the radial speed of the motor. For a torque speed characteristic, we often like to have the expression written as T is a function of U and a function of omega. So we want to have T at the left side of the equation and all the other parts on the right side of the equation. So let's do that. So we put K times omega to the left side of the equation, and we get U minus K times omega is T over K times R. So now we can say T is T on the left side of the equation, U minus K times omega, and then multiply with K over R. So T is K over R times U minus K times omega. So we can write that out. We get T is K over R times U minus K times K, which gives us K squared over R times omega. And now we can draw the motor speed characteristic, in which we draw the omega on the horizontal axis, and we put the motor torque T in Newton meter on the vertical axis. There's T, and horizontal there is omega. So when we want to draw this line between T and omega, we can start with defining intersection points on the vertical axis and on the horizontal axis. So first of all, let's look to the intersection point on the vertical axis. The intersection point takes place at omega is 0. So the right part of that equation is equal to 0. So now we get T is K over R times U. So that vertical intersection point is equal to T is K over R times U. We call that point, that torque, also the stall torque Ts, which is the maximum torque of the motor. We can also look to the horizontal intersection point. In that case, the torque is 0. So then we have an equation which says 0 is equal to K over R times U. 0 is T over K over R times U minus K squared over R times omega. Well, now we can make an expression for omega, which brings us K over R times U is K squared over R times omega. And of course, you can see that omega is equal to U over K. So what we now see is that both expressions for the intersection point on the vertical axis and on the horizontal axis have a u in its expression? Well, one remark, that speed on the horizontal axis, that intersection point, we call that the no load speed. So that is omega 0. So as I said, both expressions on the left part and on the right part have u in its expression. We can also define the slope of that straight line. And that slope of that straight line is this part, this expression, minus k squared over r. So in that part, that slope is independent of the motor speed. So now, what happens when we apply a higher voltage, what happens when we apply a higher voltage to the motor? Well, the slope stays the same because that's independent of u, but both intersection points are dependent. So with a higher u, both intersection points will increase, both on the vertical axis as on the horizontal axis. But then we get a new characteristic with a slope which is equal to the original characteristic. So let's draw it over here, the red line. Here we go. The motor torque speed characteristic at a higher u. So when u increases, the line increases, but the slope stays the same. So by applying a higher voltage to the motor, we can vary the omega, so the radiant speed of the motor. What we often do when we design a drive system, then we have, for instance, a constant torque to the motor. Well, let's call that torque Tn, a nominal torque here. And with that nominal torque, we can see by drawing a horizontal line and looking to the intersection point with the torque speed characteristic that we get an omega over here. Let's call it omega n, the nominal speed. Now, when we increase the motor voltage, then the red line applies, and then we see with the same torque, we get a new speed, which is higher than the original speed. So that is often what we do when we want to regulate the speed. Also, always take in account that when you apply a real torque to a motor, that there could be some tolerances, and when you want a specific speed, you have to take care that the voltage is high enough to realize that speed. Okay. What you often see in datasheets is that we don't have omega on the horizontal axis, but the number of rotations per minute, which is n over there. And we can calculate n by having omega, and omega dividing by 2p gives us the number of rotations per second, and then multiplying it with 60, and then we get the rotations per minute. One small remark at the end. When you look at datasheets of American motors, they often prefer to have the omega on the vertical axis and the motor torque on the horizontal axis, but all the equation stays the same and all the physics stay the same. But that's just a slightly different thing. All right. So folks, that's all. Thank you for watching and see you next time.